Okay, Chapter 2, Section 5, Basic Differentiation Properties. Okay, in the previous section, we learned about our derivative. So here it is. Here is the official definition of a derivative. If y equals f of x, then the derivative noted by f prime of x, with this little tick mark here, equals the limit as h goes to 0 of f of x plus h minus f of x all divided by h, if the limit exists. So we saw in the previous section that it takes quite a bit of work to find the derivative of functions at a particular point. And so, of course, the common question is, do you have to do it that way? And the answer is yes, you do, for that section, for this chapter. So when the first test comes along, there will be questions that say, find the derivative by using the definition of derivative, which means that this is the way you have to do it, the long way. However, we don't want to have to do it that way all the time. It would be a pain to have to do that long process every single time that we want to find the derivative. Plus, it can get really messy. The definition of a derivative, even for simple functions, can be pretty tough. So we want to find patterns. So that's what this section's about. We're going to find patterns that we get to use. Okay, so let's refresh our memories about what this means, finding the derivative of the function with a graph. So, for example, if this was our graph, say this was our f of x function here, finding a derivative means we have to find the slope of the line tangent to a point at the function, right? Always remember that. Keep that with you as we move on through these chapters, okay? So if we have a point such as this one, right? That red line is the line that is tangent at that point, right? So this describes an equation that would give us the slope of that red line would be the derivative of the function, right? The function f of x has another function that's its derivative function, and that one is a function whose output is the slope of the tangent line at any input value. Good. So the derivative is a slope generating equation. You input the input value on the domain of the f of x function, and the output of the derivative function is the slope of the line tangent at that point. Okay, but how do we find it? Okay, so let's say that we were interested in finding the slope at this point, right? So at x equals to 1.8, what's the slope of this line? The way we do it is by, first of all, finding another point on the function, say this point over here, and we want to find the line that connects those 2 points, find the slope of that line. That we can do because we have 2 points. If we have 2 points, then finding the slope is pretty easy. So we find the equation of the line that connects them. That would be this green one. So I can find the slope of that green one because I have 2 points, right? And then our goal now is to get this point to get closer and 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 closer, so that as this point gets closer to that point, right, as these 2 points get closer to each other, or if we trace it down to their input values, as the input value of this gets closer to the input value of this one, the target one, as that gap gets smaller and smaller and smaller, then we know that the slope of the green one gets closer and closer and closer and closer to being the slope of the red one, right? So let's get even closer. As we get closer and closer and closer and closer, we see that at some point, those two are going to be really, really close to each other, and then the slope of the green one becomes a really fantastic approximation of the red one. If we let that gap between those 2 points, between the 2 input values, go to 0, that's when we at 0, the limit as the gap goes to 0. Usually we use h to represent that gap between them, As that gap goes towards 0, then we find the slope of the red line. So let me label. So to be consistent with our definition, let's label some stuff here. So let's say we're interested in this point, and let's say that that's the input value A. And then we have another value over here. We're going to call that A plus H, which means that the gap between the two is H. And so we're interested in letting the limit as H goes to 0, right? We want this gap to go towards 0. As the gap between the two input values gets smaller and smaller and smaller, then this point here will travel along the function, right? So this blue one here is the function f of x. Let's call it. And let's label some points. That means that this point right here is the point a comma f of a. And that means that this point is a plus h comma f of a plus h. Okay, so we know that if we want to find the slope of the green one, the slope of the green one will be rise over run. So we can create this little triangle underneath it. And we know that the space, the change along the y-axis is going to be equal to this minus that. So we want to be able to figure out the change in the y-axis direction. So we're going to do f of a plus h minus f of a. And then we also want to find the change in this. Well, that's h, right? It's going to be a plus h minus a, minus a. The a's cancel out, which gives you just the h. So this is h. Okay, so if we want the slope of the green line, then it's rise over run. So we know that coming back over here, that's going to be equal to f of a plus h minus f of a all over h. And so that'll be the derivative of our function. That is equal to f prime at a. Okay, now one last thing, of course, algebra really loves x, and this is just a dummy variable. You know, I could have labeled this the letter B instead of A. Nothing special about the letter A. Could have been W, could have been M, could have been W, any letter at all. So of course, which letter does algebra like? It likes the letter X. So without really changing the spirit of this, we could just rewrite the whole thing in X. So f prime of x equals to the limit as h goes to 0 of f of x plus h minus f of x all over h. Right? And then all I did was change the a's to x's. So it could be any random value on the domain of our function. Okay, so this was all in the previous section, talking about the derivative, using the definition of the derivative. So if you want to find a derivative using this definition, you're going to have to set up this this quotient, and then find the limit as h goes to 0. So we saw in the previous section that can be a real pain. So in this section, we're going to look for patterns and shortcuts and ways to simplify our work. Okay, so this is the definition of derivative, and one of the most popular ways to express that we are working with a derivative is to use this notation. If y equals f of x is a function provided, then we can say this, f prime of x, to represent the derivative of that function. However, we have a few other ways of expressing the exact same thing. So if y equals f of x, then we know that f prime of x is one way of saying the derivative. So f prime of x is definitely one very popular way of saying it. Another very popular way of saying the exact same thing is just to put the y prime. Since y equals f of x, we can just express it this way. Or another way of saying it is d dx of the f function. Well, f of x function is one way of saying it. Another way of saying it is df of dx. I've seen that before as well. Another way of saying it is dy dx. And then, of course, well, you can also do d dx of y, like that. So a lot of different ways in which we can represent that we're interested in the derivative of the function. Also, note that once a specific function is described, then this kind of takes on, a couple of these take on their own style. So for example, given that f of x is equal to 3x squared plus x, just an arbitrarily selected function. Let's say given that this is that function. Of course, we can describe the derivative by saying f prime of x. But another very popular style of representing that it is the derivative is to use this notation with the f of x. So it would be d dx of 3x squared plus x, right? Where this is the function. So the d dx in front of this is letting me know that I'm interested in the derivative of this function. Another slightly less popular way of describing derivatives then is also to use that little tick mark, but apply it to the entire function. So you might see this 3x squared plus x with a little tick mark like that, indicated that we want to find the derivative of this. Okay, so lots of different ways of describing that we are interested in the derivative, that we're talking about the derivative of the function. Remembering that the derivative is the slope of the line tangent to a point, or an equation that will give us the slope tangent to a point. You know, where you input the value along the x-axis for the function, and then the output would be the slope of the line tangent at that point to the function. Okay, but why do we have so many ways of expressing the same thing? Wouldn't it be just a lot easier if we just picked one and stuck with it? Well, you know, remember that nobody invented calculus. It wasn't a single person that just sat down and created all of it from start to finish. It was dozens, if not hundreds, of people that worked on different parts of calculus. And many of them didn't even know they were working on calculus. They were just working on something they thought was kind of interesting. Many of them thought it was just kind of a unique little niche thing and didn't really see the big picture. It wasn't until later that we saw, oh, okay, all these pieces that we thought were not connected are actually just part of one big, you know, calculus book. So over the centuries, we've, you know, kind of polished it a little bit and tried to make the whole thing a little bit more fluid and you know, gotten rid of or made the notation a little bit more simple and consistent. But I think you'll agree that as you learn calculus, as we move forward through the coming chapters, that some notational styles make it easier to work with in certain areas. And so in some parts of the book, using this little notation like that makes it easier to work with. In some parts of the book, you know, using this little notation makes it easier to work with. So we've kept them all, and there's actually a couple others I'm not listing here that have maybe not as popular as these. So these are probably the most popular ways of describing a derivative, but there's certainly a couple others out there that exist. Okay, so just keep in mind there's different ways to express a derivative, and we will be using all of them in one way, shape, or other as we move forward. Okay, let's begin by thinking about the derivative of a function that is equal to the function of a constant. So, for example, if f of x equals to some constant c, What's the derivative? Find f prime of x. What is that? Okay, well, if f of x equals to a constant, remember that this is just a horizontal line for any constant, right? So for example, if f of x equals to 8, it's a horizontal line. If f of x equals to negative 3.2, it's a horizontal line, right? They're all horizontal lines. Let's graph them. So here is the line f of x equals to 7, for example. Or here is the line f of x equals to negative 3.2, for example. See, it's a horizontal line, right? Let's make it a constant, about, I don't know, p, slider. See, so if p equals any constant, it's always a horizontal line. Okay, so now what would be the tangent line? The tangent line is also the instantaneous rate of change from one point to another on our function. Well, if we just have a horizontal line, the tangent line is just going to be along that same line. And the slope of any horizontal line is always 0. Okay, so for that logic, we can conclude that the derivative of any constant, any function that's a constant, is always going to be 0. Let's look at the formal definition of a limit. So for example, now if we have f prime of x equals to the limit as h goes to 0 of f of x plus h minus f of x all over h, right? Here's our formal definition of the derivative. So let's apply this to this function. So the derivative is going to be equal to the limit as h goes to 0 of what is f of x plus h going to be when f is just the constant c. When the function equals to a constant, it means that no matter what the input is, the output is always just c. So this is just going to be c minus c, right? Doesn't matter what x is, the output is c. Doesn't matter what x plus h is, the output is c. And that'll go over h. And so we'll have the limit as h goes to 0 of 0 over h. And now you're thinking, oh, that's 0 over 0. No, not yet, because I haven't plugged in the h. I'm just simplifying this whole thing. And so this is going to be the limit as h goes to 0 of this. And, well, 0 over anything, as long as it's not 0, is going to be equal to 0. So this is just 0 before we plug in an h, right? It doesn't matter because, remember, the limit as h goes to 0 means that h is not going to be 0. We're just going to get really, really, really close to 0, but not 0. So on a point-by-point basis, this just always equals to 0. And so now the limit as h goes to 0, well, there isn't even any h anymore. So this whole thing is just going to be equal to 0. Okay, so what we established here hopefully convinced you, both using the graph as well as the formal definition, that the derivative of any constant is always equal to 0. So theorem 1, the constant functions rule. If y equals to f of x equals to c, then f prime of x equals to 0. The derivative of the function is going to be 0. And again, using our other derivative styles, then we can say that y prime equals to 0, dy dx equals to 0. We can also say d dx of c, where c is that constant, equals to 0. Right? So there's different ways of saying the exact same thing. But no matter how you slice it, if the function is a constant, then its derivative is equal to 0. Okay, so let's do some quick examples. For example, if f of x was given as the number 7.2, then its derivative would be 0, right? Easy. If the function y was equal to pi squared, I don't know what that is, but it's some number. It's just a number. Its derivative, y, is equal to 0. Okay, so you get the point. How about fraction equal to -3/4? Well, that's just some number. And so its derivative is equal to 0. If y was equal to the square root of 3, then we can write d dx of y, or we could write d dx of root 3. Either way, the answer is 0, right? Because it's a constant. I don't know what that constant, I can't write it down. I know it's an irrational number, but I know it's just a number. It's just some constant, right? Whether it's root 3, -3/4, pi squared, 7.2, it doesn't matter. These are all constants. Their derivatives are just going to be equal to 0. The graph of any one of these values, of any of these functions, is just going to be a horizontal line somewhere. Okay, so I hope that one is clear. So there you go. We got one rule right away. The derivative of any constant equals to 0. It makes it easier. Okay, so now I want to find the derivative of a couple of functions using the definition that will, one, help us practice the formal definition a little bit more, and two, we're going to start to see a pattern that develops from the functions we're going to be working with, and from that we'll be able to deduce what the pattern will be in general, and then we'll be able to establish a pattern we can use moving forward with certain types of functions so that we don't have to do it the long way every time. Okay, so let's say, for example, f of x equals to x to the power of 3. Okay, find the derivative. Okay, no problem. We jump right into our definition. So f prime of x is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h, right? So that's a good place to start. Just start by writing down the definition of it. That's what it is. Okay, so next we write down the limit as h goes to 0 of, and now we just have to evaluate our function at this point, minus evaluate our function at this point, which happens to be the same letter there. Again, it's a little confusing because we keep recycling the same letter x over and over and over again, right? Okay, so x plus h is being raised to the power of 3 minus x is being raised to the power of 3, right? I just plug this into that function there, plug this into that function there, and then the whole thing gets divided by h. Okay, being divided by h is equivalent to being multiplied by 1 over h, so I'm just going to move that out in front a little bit and then simplify my notation a little bit. So this is going to be 1 over h times, instead of dividing by h, multiplying it by 1 over h. Okay, and then I want to figure out what this is. Boy, this is messy, right? Okay, so I'm going to have to go off to the side here and figure out what this power of 3 is. There's a pattern that exists. If you know the pattern, awesome. If not, I'm just going to do it the long way here because I don't feel like going through a whole side rabbit hole thing about what that is. But if we don't know, that's fine. Let's just do it on the side here. So if you don't remember what the pattern is, then just do them one at a time here. So let's take 2 of them. That should be really easy. That pattern's easy. That's going to be x squared plus 2xh plus h squared. So now all I have to do is take that and multiply it by another copy of x plus h. So I'll have x squared plus 2xh plus h squared and multiply that by another copy of x plus h. And then together, the final answer will be equal to x plus h cubed. Okay, so let's figure out what that is. So that'll be x to the power of 3, taking this times that one, plus 2x squared h plus x h squared. So I took one of these x's and multiplied it by each of these terms. And then I'm going to take the other h and multiply it by each of those terms. So it'll be an h times an x squared. Oh, that's like this one here. So it'll be plus hx squared. That's these two. And then h times the middle one, that'll be 2x h squared. Oh, x h squared. So that'll be like this one. 2x h squared plus h to the power of 3. Good. Then we add common terms, and we end up with x to the power of 3 plus, these two are identical. We have an x squared h together, they give us a 3, plus 3 x squared h plus 3 x h squared plus h cubed. Okay, so if you remembered this pattern, great. If not, then don't worry about it. So that's what this is, right? We FOIL them all out. That's what this is right here. So this turns out to be I'll leave it in green. So this turns out to be the x cubed plus 3 x squared h plus another 3 x h squared plus h cubed. That's this term. Minus, and then, well, it's just x cubed. Nothing special there. All right, luckily this first term and that one will cancel. So this cancels out with that. And what we have left over is this. So now what we have is that this equals the limit as h goes to 0 of 1 over h. And then what survives is these three terms. So it'll be a 3x squared h plus 3x h squared plus h cubed. Good. Okay, so all of them have a factor of h. So we can factor out one h from each of these terms, and then that'll ultimately reduce with that h. So this will be equal to the limit as h goes to 0, 1 over h times 3x squared plus 3xh plus h squared. Right, so this has h to the power of 1, h to the power of 2, h to the power of 3. So if we factor 1 out, then this first term will no longer have an h. This middle term will now have h to the power of 1. And this last term now has h to the power of 2. Okay, so now, finally, these two h's will cancel. And we get to a point where we just have a polynomial. And we know that when we want to find the limit of a polynomial, it's equivalent to just evaluating that polynomial at that point. So, because this is a polynomial, we get this. The limit as h goes to 0 of 3x squared plus 3xh plus h squared, and this is just some polynomial, and so we know that this limit will be equal to evaluating that polynomial. So this is just going to be equal to 3x squared plus 3x blank plus blank squared, and we're going to put a 0 in there from here, right? So the h is a 0, so we put a 0 for the h and a 0 for the h. We do not put a 0 for the x, it's for the h, the limit as h goes to 0. Okay, but then we end up with 0 squared, that's 0. 0 times anything is 0, so both of these two terms just become 0. 0 and 0. So we end up with just 3x squared. All right, let me zoom out. Okay, so let me put that over here in a nice little box. So we had that given that f of x was equal to x to the power of 3. When we found that this was the function, that led to f prime of x was equal to 3x squared. 3x squared. Okay, let's do one more. Again, it'll help us practice with the definition, but really our goal is to start to establish a pattern, right? So keep this one in mind and we'll come back to it. Let's do the next one. Okay, so now what if f of x was equal to x to the power of 4? We did x to the power of 3 before. Now let's do x to the power of 4. Let's figure out the derivative. Find f prime of x. Right? Or they could say find dx of x to the 4th power, right? Same notational style. Okay, so let's find it. The definition, by definition. So by definition, we know that this must mean that, let's put it over here, f prime of x equals to the limit as h goes to 0 of f of x plus h minus f of x all over h. So that means that f prime of x must be equal to the limit as h goes to 0 of, and again, I'm just going to rewrite this as 1 over h times this numerator, which is going to be this. And now f of x plus h means we plug in an x plus h into that function there. So we'll end up with x plus h to the power of 4 minus x to the power of 4. Good. Now again, if you just remember the pattern for this, then fantastic. And if you don't remember the pattern, well then you can just do them one at a time. We could figure out what they are by multiplying. Let's go off to the side over here to figure out what that is. We want to do x to the power of x plus h to the power of 4. What we could do is just do x plus h squared. That's an easy pattern. Figure out what that answer is and multiply it by x plus h squared. That's one way to do it. So this would be x squared plus 2xh plus h squared. That's this one. And multiply that by x squared plus 2xh plus h squared. And then we'd have to FOIL this whole thing out and get our answer there. That's one way to do it. Or if you already remembered your previous pattern from before, we already know what that is. That one is x to the 3rd power plus 3 x squared h plus 3xh squared plus h cubed. Right? So it's a pretty easy pattern if you remember it. And once we have that, all we have to do is multiply this by one more multiple of x plus h, and that'll give me x to the 4th power. So x plus h to the 4th power is the same thing as x plus h to the 3rd power times x plus h. And we already have that x plus h to the 3rd power is this thing. So I end up with the product of x to the 3rd plus 3x squared h plus 3xh squared plus h cubed. That's this one. Times x plus h, right? And so now I have to multiply each one of these by an x, and then come back and multiply each one of these by an h. So if I raise all the x powers by 1, I get x to the 4th power plus 3x to the 3rd h plus 3x squared h squared plus xh cubed. And now I come back and multiply each one of these by h, or raise the power of h by 1. So I end up with an x cubed times h, which is like this one. So x cubed h plus, and it'll be x squared h squared plus 3 x squared h squared. And then this one's going to be xh to the 3rd power plus 3xh cubed, finally, plus h to the 4th power. Okay, so now we just combine like terms. and we see that we get x to the fourth power plus 4x to the third h plus 6 x squared h squared plus 4 x h cubed plus h to the fourth power. Okay, so again, if you remember the pattern, then you don't have to do it this long way. That's fine. It's not a very difficult pattern to remember. But I'm not going to spend more time on that. That's a separate little rabbit hole I can go down. But at any rate, so that's what it is. So let's come back over here and rewrite what this is back in our equation. So back to this guy. I want to find the derivative. So the derivative with respect to x is going to be the limit as h approaches to 0 of 1 over h times, now that first one, let's put it in green so it's clear. It's x to the fourth plus 4 x h to the third plus 6 x squared h squared plus 4 x to the third h to the first plus h to the fourth. All of that minus x to the fourth. Okay, so that's what that is. And again, luckily, the first term and the last term will cancel. And these are the only survivors. So we get f prime of x is equal to the limit as h goes to 0 of, and then we have a 4xh to the third power plus 6x squared h squared plus 4x to the third h plus an h to the fourth power. Okay, again, all 4 of these terms have an h in common. So let's, oops, there's a 1 over, forgot the 1 over h out in front from there. So let's factor out an h from the numerator, and we get that f prime of x is equal to the limit as h goes to 0 of 1 over h times, and we can factor out an h from all of those values in the numerator, giving me a 4xh squared plus a 6x squared h to the power of 1 plus a 4x to the third power plus h to the third power. Right, so I lowered the exponent by 1 for all of these, the exponent on h by 1. And then, of course, this one only had one h, so it's the only term that doesn't have an h anymore. Okay, now these h's cancel. This guy cancels with this guy. And what we're left with is that the derivative then is equal to the limit as h goes to 0 of 4xh squared plus 6x squared h plus 4x cubed plus h cubed. Okay, and the result now is this polynomial. And as we know by now, when we're trying to find the limit of a polynomial, we can just evaluate. Because it's a polynomial, the limit is equal to evaluating it at that point. So that means that derivative is going to be equal to 4x blank squared plus 6x squared blank plus 4x cubed plus blank cubed. And the thing we're going to plug in there is going to be this 0, right? The h gets replaced by a 0. Okay, well, 0 squared is 0. 0 times anything is 0. So that means this first term is going to be 0. This second term is going to be 0. And this last term is going to be 0. So the only thing that survives is this. And that's our answer. So we get that f prime of x is equal to 4x cubed. Okay, so if f of x is equal to x to the fourth power, and we're asked to find the derivative using the definition, here it is. Long, ugly thing. And yes, this is exactly how I expect to see it on the test, right? Be careful with the notation. I've already seen a few of you have kind of been asking me about your work, so I've seen a few of you, the work that some of you are doing, and you're missing all of this out, right? You can't just solve it sort of like scratch work on the side and not come back and organize it, right? So in order for it to be a proper mathematical statement, you need to put that f prime of x equals the limit as h goes to 0, and that kind of travels along from one line to the next line to the next line to the next line until we get to identify when it disappears. And it gets to disappear when we get to a point where we have a polynomial that we can evaluate. Also, it could be a rational function where a rational function where the value 0 for h can be replaced and not result in a 0 in the denominator. Okay, so we've seen so far that when f of x is equal to x cubed, it turned out that its derivative, f prime of x, was equal to 3x squared. Okay, and then we did the work to figure out that if the original function is x to the 4th power, its derivative, f prime of x, is equal to 4x to the 3rd power. Okay, so do we start to see a pattern? Based on this, can we guess what the next one is going to be without actually doing the work? You see that when we have x to the 4th power, the derivative was 4x to the 3rd. When we had x cubed, x to the 3rd power, its derivative was 3x to the 2nd power. So is it clear that a pretty good guess, and that's all it is at this point, a guess would be that the derivative of this thing would be equal to 5x to the power of 4. Right? And the one after that, f prime of x to the 6th power, its derivative, well, just following the pattern, it looks like whatever the exponent was comes out in front as a constant, as a numerical factor, coefficient, as a numerical coefficient, and then we lower the power of the variable by 1. Right? So 3 leads to 1. 4 leads to a power of 3. Power of 5 leads to a power of 4. So just following that pattern, I see that this leads to that. Good. And then coming back, well, then that would have meant that this one, x to the 2nd power, would be f prime of x equals to 2x to the power of 1. And if we just had f of x, right, we can think of that as a 1 there. That leads to f prime of x is equal to 1 times x to the power of 0, since we go down by 1 power, or x to the 0 power is just going to be equal to 1, so it just equals 1 in that case. Okay, so we have a pattern established here, and so if we just keep going along this path, we go dot, 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 dot. Let's write it down in general. So in general, if I was going to have some power of n, so I have f of x equals to x to the power of n, then the pattern is going to be that its derivative is going to be equal to n times x to the power of n minus 1, right? We bring the, whatever number is there, we bring it out in front, and then we subtract 1 from the exponent. Okay, so this is the pattern that we've established. We proved it, we've shown that it worked for x to the 3rd power and x to the 4th power, and then we looked at the pattern, and based on the pattern, it seemed reasonable to conclude that this is how it works when we have x to the power of a constant, like these cases, and we extend that to a general statement like this one. Okay, so we can formalize that in the following theorem, the power rule. If y equals to f of x equals to x to the power of n, where n is any real number, then the derivative of f prime of x, is equal to n times x to the power of n minus 1. right? Just like we've already established. And then also, again, just to refresh your memory, there's a variety of ways in which we can express derivatives. So we can say y prime is equal to nx to the power of n minus 1, or we can say dy dx equals to n times x to the power of n minus 1. Remember or note that I only showed it for the cases where n was counting numbers. We did it for x to the third, x to the fourth, and then from that we kind of established the pattern. But there's a more robust rule that says that actually it'll work the same way no matter what this is. So we haven't proved it. I just showed it worked for x to the third and x to the fourth, and that's not really a mathematical proof. But the proof for this is a little on the, it's outside the scope of this class. So we're not going to cover the proof, and you're not responsible for the proof. You just have to understand what this means and use it and apply it, and we'll move on. But you must trust that there is a proof out there, right? All of this is safely built on solid mathematical foundations that can show that this is true. Okay, so let's do some examples that use this. Okay, so for example, if we were given f of x equals to x to the 8th power, find f prime of x, right? Find the derivative. Yes, of course, we can always go back to our definition. So, of course, if you love the definition and you want to go back to this thing, the derivative of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h, right? And so you can just go back to this definition if you really like it, but we have a pattern. We know that if we have something that fits this form, if we have something that fits the form f of x equals to x to the power of n, we know its derivative is just equal to nx to the n minus 1. Bring the exponent out in front and subtract 1 from the exponent. So that's what we can do here, and that's good enough to solve the derivative. So what we have is this: f prime of x is equal to 8x to the power of 8 minus 1, right? And then we can just simplify that and say f prime of x is equal to 8x to the power of 7. Good? Okay, so this is good enough unless the problem specifically said using the definition of derivative. By default, if it doesn't say using the definition of derivative, then you're allowed to use the shortcuts. And we're going to develop a lot of shortcuts. The next few sections are going to be chock full of shortcuts to derivatives, so we don't have to use the definition. But remember that we do have to learn the definition because on our test there will be some questions that say you must use the definition of derivative to find it. So make sure you know how to do that. But once we get beyond that section, once we leave this chapter, moving forward, you'll be allowed, and in fact you'll be expected to use the shortcuts, because otherwise it becomes really difficult to do the problems moving forward. Okay, all right, so it's a simple pattern. Move that exponent out in front, becomes a coefficient, and then we subtract 1 from the exponent. So remember that I said that n doesn't have to be a counting number, though. It could be anything at all. So let's try a different one. Okay, now let's try f of x equal to x to the power of 37. Nice big number. Using the definition would involve something about x plus h raised to the power of 37. So that already would be very difficult to do it by hand, right? So by the definition, to find the derivative, find f prime of x. If you wanted to stick to the definition, we know that that would mean that we'd have to solve this. The limit as h goes to 0 of f of x plus h minus f of x all over h, which would mean we'd have to have an x plus h raised to the power of 37 minus x raised to the power of 37 all over 37. the limit as h goes to 0 of this thing. Already a pain. Ugly, right? But we could do it if we wanted to. Keep going, keep going. Okay, but we do have the benefit of these shortcuts, right? So shortcut makes it really, really easy, the power rule. So given that f of x equals to x to the 37th power, then we know that this is just going to be 37 times x to the 37 minus 1 power, which can be simplified to 37 times x to the 36 power. Right? Very easy. Let's try another one. What if f of x was equal to x to the power of negative 4? It doesn't have to be positive constants, natural values or counting numbers. It could be integer values as well. So just using that rule, we know that this must be f prime of x is equal to, bring that exponent out in front, so that becomes a negative 4, times x to the minus 4 minus 1. Now we just have to be careful about the exponent. So most people write this as minus 3. But remember, we're subtracting 1 from the exponent. That means we go deeper into the negatives. So our derivative becomes negative 4 times x to the negative 5 power. What if f of x is equal to x to the power of 2/7? Okay, so just keeping with a pattern, this fits the form of f of x equals to x to the nth power, and we know that its derivative is going to be nx to the n minus 1. And this is for n being a member of any real number, right? Capital R with an extra slash is all real numbers, for any real number. And 2/7 is a real number. So we just follow that same pattern, and we can conclude that f of x is equal to 2/7 times x to the 2/7 minus 1. Right? Subtract 1 from that exponent. Okay, so we just have to do a little bit of algebra now and figure out what that is. So I can say, oops, this is the derivative is equal to this. So f prime of x is going to be equal to 2/7 times x to the 2/7, and I'm just going to replace that 1 with a 7/7 to get a common denominator, 7/7, which then gives me f prime of x is equal to 2/7 x to the power of negative 5/7. Okay. So we could leave it like this, or of course we can take advantage of our algebra skills and note that when we have a negative in the exponent, we can rewrite it by writing it underneath 1. So this is the same thing as f prime of x is equal to 2/7 times 1 over x to the power of positive 5/7, or finally x is equal to one big happy fraction where there's just a 2 up there, and there's a 7 times an x to the 5/7 in the denominator. Right? So they're all good. So if it says make sure you simplify your answer all the way, usually simplify your result means that we use our algebra skills to manipulate it so we don't have a negative in the exponent. So this would be the most simplified version here. Most popular answer. If you look in the back of the book, this is probably what you'll find. Okay, let's do another one. What if f of x is given as 1 over x to the 5th power, and we want to find its derivative? Find f prime of x. Okay, so the first thing I'd want to do is manipulate this a little bit so that it fits our standard form. because I don't know anything about this the way it looks exactly, but I do know that we have our power rule that if f of x is equal to x to the nth power, we know that its derivative is going to be n times x to the n minus 1. Right? So we know this, and n is allowed to be any real number. Any real number. So if I can just manipulate this a little bit and rewrite it like that, I can rewrite it this way: x to the power of negative 5. 1 over x to the 5th power is equal to x to the power of negative 5. And now it fits that form. So now I can find the derivative. F prime of x is just going to be equal to negative 5. Make sure you bring that negative with it. X to the negative 5 minus 1. And so we get f prime of x is equal to negative 5 x to the minus 6 power. And as we saw before, we can simplify that by rewriting it this way. Minus 5 times 1 over x to the positive 6 power. Or finally, one big happy fraction with a minus 5 in the numerator and an x to the 6th power in the denominator. So probably the most popular version of it is this one. So we're technically done at this point. So you might see this as a pretty common answer as well. But again, if it says simplify it as much as possible, often the interpretation of simplify as much as possible means that we get rid of all negatives in the exponents. So if you look in the back of the book or something to confirm some of your homework answers, you might find that it's written this way or that way. So we have to be able to go back and forth. Okay, what if f of x is equal to the square root of x? Find its derivative. Okay, so just like before, we want to manipulate this a little bit. And again, we want to use the power rule, knowing that if f of x is equal to x to the nth power, then its derivative is going to be equal to nx to the n minus 1. And this is where n is any member of the real number set. Okay, well, this doesn't quite look like that right now, so we have to manipulate it a little bit. Luckily, we remember from algebra that the square root is equivalent to x to the power of 1/2. Right? That 1/2 there is this invisible little 2 here. So if there's others, so for example, cube root of x is equal to x to the 1/3 power, and the 5th root of x is equal to x to the 1/5 power, as we see this pattern. And if we see the square root of x, well, square root of x is the same thing as having this little invisible 2 there. By default, if we don't see anything there, blank, then it means that there's a little 2 there. And so this equals to x to the 1/2 power. So hopefully that looks familiar. And so if we manipulate it a little bit, then we have something that does fit this form. So now following our pattern, we can find the derivative pretty easily. This turns into 1/2 x to the power of 1/2 minus 1. Bring the exponent out in front like a linear factor, and then we subtract 1 from the exponent. So now simplifying it, we get that the derivative is equal to 1/2 x to the power of minus 1/2. And so simplifying that, we get f prime of x is equal to 1/2 times 1 over x to the positive 1/2 power. And so f prime of x is equal to a giant fraction where there's a 1 in the numerator and then a 2 square root of x. Okay, so that's probably the most popular way in which this answer is written. What if this was the function? 1 over the 5th root of x. Find the derivative, f prime of x. Well, again, using the same power rule, we know that If f of x is equal to x to the nth power, then we know that the derivative is equal to n x to the n minus 1. N gets to be any real number. Okay, so we just have to manipulate this a little bit. Luckily, we know that the denominator can be rewritten as 1 over x to the 1/5 power. That's what that means. And we know that we can bring this up to the numerator by introducing a negative in the exponent. So this is equal to x to the power of negative 1/5. Good. So now that it looks just like that, here the n equals to negative 1/5, we can follow the same rule. And now we just have to find what that is. So getting a common denominator of 5 over 5, we get that our final answer for this difference is x to the power of negative 6 over 5. Good. Which means that we can again simplify this using our algebra skills as negative 1 over 5 times x to the power of positive 6 over 5, which then can be reduced as rewritten as negative 1 over 5 times the 5th root of x to the 6th power. So this is very popular, so is this, so is that. It depends on the author of the book and who you're talking to. This is pretty useful to work with it this way, but you know, if you look in the back of the book and look for your answers to make sure they match, you might see that it looks like this. So they're all equivalent to each other. Okay, so that was lots of different examples of how to use the power rule to solve a variety of functions that can apply the power rule. What does that mean? Is differentiable of x? Well, that means that the derivative exists, right? This little sentence here means that f prime of x, which is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h, that it's a valid thing. It exists. Right? Just assume that that's true. There's a function and it's differentiable. It means that this is true. Okay. Also, let k equal any constant. Any constant at all. Okay, so now what we want to do is think about a new function, g of x. Let's let g of x be equal to k times f of x. A constant, any constant like 7 or 13 or pi, any constant times our function, which we know to be differentiable. What we want to do is use our definition of derivatives to find the derivative of g prime of x. So now, find g prime of x. So by definition, as h goes to 0 of g of x plus h minus g of x all over h. Good. So all we have to do is evaluate our g function at this input. Now that looks a little tricky, so if we want to evaluate at this input into this function, right, the g function input is just going to be the f evaluated at that input times k. Good. So this just turns into k times f of x plus 1. That's g of x, oh sorry, not plus 1, plus h. That's what this is. Inputting x plus h into this function is just k times f of x plus h. Minus, now inputting the x, well that's just this. That'll be k times f of x. All of that gets divided by h. We still have our limit as h approaches to 0. And that is our derivative. Okay, so what we want to note is that we can factor out this k from there, and there's a k there. We can factor that out. So this is going to be equal to the limit as h approaches to 0 of k times, and then this is f of x plus h minus f of x divided by h. And if we look at our rules for limits, we know that if we have a constant times a function, we can bring that constant out in front. This limit, as h approaches to 0, has nothing to do with that one. If this was just an h out here, you couldn't ignore it and put it out in front. But because it's a variable that has nothing to do with that h, we can just pull it out in front. So this is equal to k times the limit as h approaches to 0 of f of x plus h minus f of x all over h. So this is, g prime of x. So g prime of x equals this. And, well, all of this right here, this is the derivative of the f function. Now, I don't know what it is, but I know it exists. So I can just refer to it. And so we can conclude that g prime of x is equal to k times f of x. Okay, let me zoom out. So if we are given that the function f of x is differentiable at x, so that's something that we know to be true, the derivative exists, and k equals any constant, then if we define a new function g of x equal to k times f of x, and we want to find the derivative of g of x, so g prime of x, by definition, we can follow this process and end with this, right? So what is this saying? It's saying that if we are given a g function, which is a multiplication of a constant times a function that we know is differentiable, then we can just multiply the constant times the derivative of that function, right? That's what this is saying. Let me formalize this with a theorem. So theorem 3, the constant multiple property. If y equals to f of x equals to k times u of x, then the derivative of f of x is equal to k times the derivative of u of x. So that's what we've established. If we have k times a function and we know that function has a derivative, then the derivative of this f function is equal to k times the derivative of the u function. That's what this is. And of course, we have a variety of other notation styles to represent the same thing. So we could also say y prime is equal to k times u prime, or we can say dy dx equals to k times du dx. One more way to represent the same thing could be to say that if we have y equal to k times the u function, right? So this is the function y is equal to k times the function u. Then we can say d dx of y is equal to d dx of k times u. And then we can pull that out in front and say that this is d dx of the y function is equal to k times d dx of the u function. Good. And so this simplifies into that. So this could just be dy dx is equal to k times du dx. Okay, it looks complicated, but this is a really simple thing. It just allows us to pull out a constant out in front of a function and deal with the function itself. Let's look at an example. For example, if we had f of x equals to 5x to the power of 3, we know that x to the power of 3 is something that is differentiable, and we know that we can use the power rule to simplify it. So now if we want to find the derivative of f of x, then all we have to do is multiply 5 times the derivative of the function that's differentiable. So f prime of x is just going to be equal to 5 times and then the derivative of that second function. So the derivative with respect to x of the x cubed. Good. So all I did was separate the 5, the constant, and now I'm going to find the derivative of this part. See how this notation is useful in this case to really clarify that I'm going to now go ahead and find the derivative of this. So the derivative equals to 5 times, and we know the power rule here just tells me that this is 3 times x to the 3 minus 1. So this is going to be equal to 5 times 3 x to the second power, which then can just simplify to 15. So it becomes 15x to the second power, right? And that's our final answer. Say f of w equals to w to the 4th power over 3. Remember, x is just a dummy variable. There's nothing special about it. So instead of x, we can use w. Okay, so then again, we can think of this as a constant times w to the 4th power. So this is the same thing as one-third w to the 4th power. And now we can say that the derivative of this function is equal to 1/3 times the derivative with respect to w of w to the 4th power. Notice that I'm changing all the things with x over to a w. ddw of w to the 4th power. Okay, and so now we know that if we follow our power rule, this is going to be 1/3 times 4w to the 3rd power. And so our final answer is going to be 4/3 w to the 3rd power. Again, we don't have to use x. Nothing special about x. We could use the letter n. So f of n equals to 1/3 times n to the 5th power. Again, we can simplify this a little bit using our algebra skills and say that this is equivalent to 1/3 times n to the power of -5. And so now this falls under the power rule, and we have a constant times a function that is differentiable under the power rule. So now its derivative, f prime of n, is going to be equal to 1/3 times the derivative with respect to n of the n to the -5 power. And so f prime of n is equal to 1/3 times, and now we use the power rule here. This is going to be equal to -5 n to the -5 minus 1. Right? Bring that down, subtract 1 from the exponent. And so this becomes f prime of n equals to -5/3 times n to the power of -6. And so we can simplify that a little bit by getting rid of that negative in the exponent, and this becomes one big fraction, the -5 in the numerator, and 3n to the 6th power in the denominator. Just in case this n is confusing people, I know it's hard to wing off the x's, right? So let me rewrite it real quick here with just x's to see how it would have looked, right? Particularly this right here. So, or f of x equal to 1/3. So this is how the problem would have looked if we used our favorite letter x instead of this n. So it takes a little bit of time, I think, to get used to using different variables, especially when it comes to this new notation we just learned, that this represents the derivative of our function with respect to the variable, which in this case, the independent variable is x. So we write ddx of our function written in x. But here, if we're using the letter n, then we need ddn We need the derivative with respect to the letter n, where n is our independent variable described up here. Okay, so it's just a dummy variable. X, y, w, n, doesn't matter. We just have to be consistent and hopefully, get used to the notation. What if we had 0.5 over the fifth root of x to the third power? Find the derivative. Again, we're just going to manipulate this a little bit to simplify it. So that means that f of x is equal to 0.4 over x to the power of 3/5. F of x is equal to 0.4 times x to the power of negative 3/5. And so now this is a function that falls under the power rule. So now when we want to find its derivative, negative 3/5 minus 5 over 5, which becomes negative 8 over 5. And I'm going to simplify this, so I'm going to go ahead and rewrite this as 4 over 10. Get rid of that decimal. 0.4 is the same thing as 4/10 times negative 3 over 5. I know nothing is really going to reduce here, so I'm just going to go ahead and multiply 4 times 3 over 5 times... Oh, well, this reduces a little bit. Never mind. Okay, so I know this is going to reduce. There's a 2 there, and there's a 5 there. And then nothing else reduces. And then here, this turns into times x to the power of negative 8/5. So the derivative f prime of x becomes a giant fraction where we have negative 6 in the numerator divided by 25 times the fifth root of x to the 8th power. Okay, so the power rule is very, very useful. And we can use it, we can apply it in many cases where we can just manipulate the original statement by a little bit to make it fit a form that allows us to use the power rule, right? That coupled with the theorem that indicates that if we have a constant in front of our function, we can just ignore the constant, put it out in front, take the derivative of the function if it's differentiable, and then we can find those derivatives. Okay, so hopefully this is clear enough. Given that f of x and g of x are differentiable, at x, let's define this new function w of x to be equal to f of x plus g of x. Okay, so it's a new function defined to be as the summation of these two known functions, these two given functions, and we know that those two functions are differentiable at x, their derivative exists. Okay, so now let's find the derivative of this w function. Find w prime of x, the derivative of this new function. So by definition, we know that w prime of x is equal to the limit as h goes to 0 of w of x plus h minus w of x divided by h. Okay, well, plugging this into there means that we get f of x plus h plus g of x plus h. So this is going to be equal to the limit as h approaches to 0 of f of x plus h plus g of x plus h minus parentheses f of x plus g of x. all over h, right? In other words, this part right here, finding w of x plus h, well, the w is the summation of these two functions, so all of this right here is this one, w of x plus h. And the w of x, this one, well, that's this. Don't forget to put a subtraction there. And all of that goes all over h. Okay, well, we know that we can simplify this. This is equivalent to the limit as h approaches to 0 of f of x plus h plus g of x plus h minus f of x minus g of x all over h. And we know that we can move around the order of these things as long as we keep track of the sign. So we can make this equal to this, the limit as h approaches to 0 of f of x plus h minus f of x plus g of x plus h minus g of x, right? So all I did is swap around the order here, keeping track of the sign. All of that still stays all over the h. And now we can separate this into two pieces. This is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h plus the limit as h approaches to 0 of g of x plus h minus g of x all over h, right? Our rules for limits tell us that we're allowed to do this. And now what we have is that this is exactly equal to the derivative of the function f. So this is f of x, f prime of x. And this is exactly, by definition, equal to the g of x. So I don't know what it is, but we started out by saying, given that we know the derivative exists. So we have, let me zoom out, this was the w. So given that f and g are differentiable at x, and if we define a new function, w of x equal to f of x plus g of x, and we want to find the derivative, w prime of x, the derivative of the w function, then we can follow our definition and conclude that the derivative is equal to the derivative of the w function is equal to the derivative of the f function plus the derivative of the g function. Good? Okay, well, a similar thing will happen if we have a subtraction instead of an addition. So if we come back up here, and all we do is say, well, no, okay, let's start with a subtraction of these two functions instead of an addition. Then there will be a subtraction there, and there'll be a subtraction there, which means there'll be a subtraction there, and then there'll be a minus here, and then this will turn into an addition there, and then we'll move things around and factor stuff out, and at the end of the day, we'll see that there will end up being a subtraction there. So we can bring this all together into the following theorem. The sum and difference property. If y equals to f of x, which is equal to u of x plus v of x, then the derivative of the f function, f prime of x, is equal to u prime of x plus or minus v prime of x. So what we can get out of this is that if we have a summation of two different functions, right, we have one function is equal to the summation or difference of two different functions, and we want to find the derivative, then we can just take turns and then add or subtract them, and then just add them or subtract them separately. For example, let's say that the u of x function is equal to 5x to the third power, and let's say that the v of x function is equal to 2x to the fifth power. So now if we define this new function, f of x equals to u of x plus v of x, or f of x is equal to 5x to the third power plus 2x to the fifth power, and you're asked to find the derivative. To find the derivative f prime of x. Well, according to this theorem, right, we have one function here, another function there. They're just separated by this addition. According to this, I can just find the derivatives of each one of them separately and then add them together, right? So that makes this really easy. So we know how to find this derivative. We know how to find that derivative. The derivative of the whole thing is equal to the derivative of the first part plus the derivative of the second part. Good. And now that's really easy to find. So f prime of x is equal to 5 times 3 x to the second power plus 2 times 5 x to the fourth power. Good. So now I can just simplify it and say that f prime of x is equal to 15x squared plus 10x to the fourth power. Okay. All right, more examples. So for example, if the function f of x is defined as 7 plus 4x to the negative 3 power minus 8x to the third power, well, technically this is a summation or a difference of 3 separate functions, and each one of those functions fits under the power rule, so we know that each one of those is differentiable, right? So we know that if we had u of x equals to 7 and we had w of x equals to 4x to the minus 3, and we had v of x equal to 8x to the third power, each one of these is differentiable by the power rule. And so what we have here is some function that is being described as a summation or a subtraction of other functions that we know are differentiable. This is equal to u of x plus w of x minus v of x. Okay, we don't have to do all this work every single time. I'm just pointing out that this is really very easy to find if we use our theorem. So f prime of x is then really equal to the derivative of the u function plus the derivative of the w function minus the derivative of the v function. Right, so we can just find each one of them separately. Well, we know that the derivative of the u function, well, that's just going to be 0 because that's a constant. We know that the derivative of the w function, well, that's going to be equal to negative 8x to the negative 3 power. Right, multiplying negative 2 times 4 makes it negative 8. To the power of subtracting 1 from the exponent brings you over to negative 3. And finally, v prime of x is equal to 24x to the second power. Right? And so you bring those in here, and we get f prime of x is equal to 0 plus negative 8x to the negative 3 power minus 24x to the second power. Okay, well that 0 doesn't do anything, so we can just get rid of it. And so my final answer would be negative 8x to the negative 3 power minus 24x to the second power. Okay, well nobody ever writes it this way. This is an overkill for sure. Defining each piece as a separate function, taking the derivative of each one, coming back, redefining our function as a summation of these other functions. Okay, people don't really do that. So hopefully this is helpful to see the pattern. But moving forward, never do this unless you're asked to do it that way. But all we have to do is the following, and it's really easy. 4x to the negative second power minus 8x to the third power. Well, all we have to do is take the derivative of each one. We want to take the derivative with respect to x of the 7 plus the derivative with respect to x of the 4x to the negative 2 power minus the derivative with respect to x of the 8x to the 3rd power. Right? We just take the derivative of each one separately when they're separated by additions or subtractions. So you don't have to do this whole thing of defining them as separate functions. I was just pointing out how it fits into our theorem. Okay, well, now we can just find these derivatives. So f prime of x gives you a 0 for that one, plus a negative 8x to the negative 3 minus 24x squared. And so from there we can conclude that this is equal to negative 8x to the negative 3 power minus 24x to the 2nd power. And now this might be good enough, or you might be asked to simplify it because the negative in the exponent. So this could be rewritten as negative 8 over x to the 3rd power minus 24x to the 2nd power. And again, that might be good enough. Or they might ask you to bring it all together under one big happy fraction, which means we'd have to multiply numerator and denominator by x to the 3rd power. So times x to the 3rd over x to the 3rd. And so we could arrive at our final answer. Prime is equal to one big happy fraction where the denominator has an x cubed and the numerator has minus 8 minus 24 x to the 5th power all over x to the 3rd power. So this is a perfectly good answer. So is this part before we decided to multiply the numerator and denominator by root x to the 3rd over x to the 3rd. Or maybe this, right? So it depends on how far we need to go to simplify things. So technically the derivative is done there, but to get rid of that negative in the exponent, we have to take the additional steps to simplify it and get to this point here. Okay, so on the test, for full credit, you will have to manipulate it a little bit, at least to this stage, right? We don't want to give answers that have negatives in the exponents. Okay, so this property really makes it easy to deal with any polynomial, right? Any polynomial is the sum of terms, and each one of those terms can fit the power rule. So this really just allows us to solve any polynomial really quickly, really nicely, and then some, right? Some even more complicated functions. So let's try a couple more. Let's say f of x is equal to the 5th root of x minus 2x to the 3rd power. Okay, so we can manipulate this a little bit. So I'm going to manipulate this a little bit before I find the derivative. I'm just going to rewrite this as x to the power of 1/5 minus 2x to the 3rd power. And now I know that the derivative with respect to x of this function is equal to the derivative with respect to x of this, x to the 1/5, minus the derivative with respect to x of the 2x to the 3rd power. Right? Our function says, well, our theorem says, just find the derivative of each one separately and then subtract your answers. And each one of them is differentiable because each one of them qualifies under the power rule. So we got that the derivative is equal to, following our power rule, that's going to be 1/5 x to the power of 1/5 minus 1 minus, and then this is going to be equal to 2 times 3 x to the 3 minus 1. So simplifying that, we end up with 1/5 x to the 1/5 minus 5 over 5 minus, and this is going to be 6 x to the power of 2. And then we get to go to, this is equal to 1/5 x to the power of negative 4/5 minus 6x squared. And so if we just get rid of that negative in the exponent, we can get to something That looks pretty good. It's going to be 1 over 5 x to the 4 fifths, positive 4 fifths, minus 6x squared. Okay, so that's pretty good. At least we got rid of the negative in the exponent. So as long as you get rid of the negatives in the exponents, I'm happy with the answer. So this looks good. Or another popular version of this would be to say that this is then equal to, using the roots, this is equal to 1 over 5, and then it's the 5th root of x to the 4th minus 6x squared, right? Using the root notation, very popular as well. And then we could, again, figure out a way to combine them and make them into one big happy fraction. And to do that, we'd have to multiply the numerator and denominator of this fraction by that. So that should be not too bad. This will be equal to 5x to the 4 fifths all over 5x to the 4 fifths. So we end up with, so from here we can get that f prime of x is equal to one big happy fraction, where in the denominator we're going to have this 5x to the 4 fifths, and in the numerator we get 1 minus 6x squared times 5x to the 4 fifths. And now we just have to combine these two. Remember that when we're multiplying exponential numbers with the same base, all we have to do is add the exponents. So this is going to be f prime of x equals to 1 minus 30 x to the power of, so I have to add these two. I have to add the 2 and the 4 fifths. Let's figure out what that is off on the side here. So if I just figure out what is 2 plus 4 fifths, common denominator of 5, let's multiply it by 5 over 5. We get 10 over 5. That's going to be 10 over 5 plus 4 over 5. So we end up with 14 fifths. Okay, so that's what the summation of these two is, 14 fifths. So let's put that here. 14 fifths all over 5x to the 4 fifths power. Okay, so this is just algebra, right? A messy algebra problem at this point. So the calculus part of it ended a little while ago when we finished our derivative. We just had to find a way to simplify it. And then, of course, we could do one more step here and rewrite this as using the root notation. So one last way of writing this would be f prime of x equals to one big happy fraction where we have 5 and then the 5th root of x to the 4th power, and then 1 minus 30, and then the 5th root of x to the 14th power. Whew. Okay, lots of fun ways to represent this, and they're all the derivative. Okay, so let me zoom out. Zoom out. Okay, if you're wondering, well, which one do I have to do? Well, for the homework, well, you should be able to do them all. You should be able to manipulate them algebraically from here to here to here and to here. But for the homework, look in the back of the book or Chegg or wherever you're finding your answers to confirm that it matches the answer. So if you look in the back of the book and this is the way it's written, then you need to be able to manipulate this to make it look like that. Or maybe it's written this way. So you, again, need to be able to do the manipulation to be able to get it to look like that. So that's a good meter stick. Make sure it matches whatever the solution is. Another sort of guideline is in math, if the original question was given using this style of notation, the fifth root like this, then we would like our final answer to kind of match it. On the other hand, if the original question was given already with a fractional exponent, then our final answer should match that as well. So that could be a clue of what the final answer should be. And most importantly, on the exam, what do I want? Well, follow the instructions. If I say simplify it all the way, I might say, make sure you simplify it all the way and leave fractional exponents or positive fractional exponents, or I might say make sure you use root notation. So, follow the instructions. I would normally accept anything. The only thing I really usually stop at is accepting negatives in the exponents. But follow the instructions to get full credit, right? The instructions on the test. Good. If there's no instructions, then by default, you'd want to get rid of negatives in the exponent. That's really the only thing that's pretty consistent throughout math. We don't like negatives in exponents. Okay. Another example. Okay, so if f of x is equal to this, and we want to find its derivative, f prime of x is then going to be equal to the derivative with respect to x of the first term minus the derivative with respect to x of the middle term plus the derivative with respect to x of the last term. Right? And then each one of these we can simplify. This is the same thing as the derivative with respect to x of 2/3 x to the negative 2. Right? I haven't found the derivative yet. I've just manipulated this a little bit to make it look like that. Minus the derivative with respect to x of x to the minus 4th plus the derivative with respect to x of 1/11 x to the second power. Right? I haven't found the derivative yet. That's why I still leave this notation here, meaning that I have to find its derivative. Okay, so now I find the derivative, and that's how I get rid of that notation. Okay, so then following our power rule, they all qualify under the power rule. So this is going to be equal to 2/3 times negative 2 x to the negative 2 minus 1 minus, and then this is going to be minus 4 times x to the minus 4 minus 1 plus, and this is going to be 1/11 times 2 x to the 2 minus 1. Right? Just using that power rule. So this is equal to negative 4/3 x to the negative 3 power plus 4 x to the negative 5 power plus 2/11 x to the 1 power. Good. And then again, getting rid of the negatives in the exponents, x is equal to negative 4/3 1/x to the 3rd power plus 4/x to the 5th power plus 2x/11. Okay, well, at least we got rid of the negatives in the exponent, so that's a pretty good answer. Or they might want you to bring it together under one big happy fraction. Again, follow the instructions. If we wanted to do that, we need a common denominator. And so that common denominator is going to be to make sure all the fractions have an x to the 5th, and that all fractions have a factor of 3, and that all fractions have a factor of 11. So we're going to multiply this one by x squared over x squared. That's a new version of 1. And then I also need the 11, so times 11 times 11. And then this one I need the times 3 times 11. I need the times 3 times 11, or 33. And then this one, I need an x to the 5th power over x to the 5th power, and I'm also missing that 3, so 3 over 3. Okay, so all of that simplifies to f prime of x is equal to negative 44x squared all over 33x to the 5th plus 132 divided by 33x to the 5th plus 6x to the 6th power divided by 33x to the 5th power. And now, since they all have that same common denominator, we can come up here and say that f prime of x is equal to one big happy fraction, where we have a minus 44x squared plus a 132 plus a 6x to the 6th power, and all of it gets divided by 33x to the 5th power. Okay. All right, so that's just algebra, though. This part here, from there to there, is where the calculus ended, right? So this is the derivative. We found it. We just need to simplify it a little bit. And there we go. Okay, so the point is that if we have a complicated or a long function that's divided up, broken up by addition and subtraction signs, that we can just find the derivative of each one separately, find those answers, and then add them or subtract them to get to our final answer. Once we do that, then it's just a matter of algebra to figure out how to simplify it and reduce it down to the form that that is needed to submit your work. Okay. Most important part right now is to get used to the notation, right? Please fight the urge to want to take weird little shortcuts that we're not allowed to use yet, and also remember that the goal is not to find the answer, right? I often get a whole bunch of sort of gibberish off to the side that I can't figure out heads or tails of, and then all of a sudden it all comes together and there's the answer. You'll get partial credit there, but in order to get full credit, it needs to be something that can be read from line to line to line to line. So make sure you practice doing that on your homework so you can get full credit on the test. Okay, we need full mathematical sentences from line to line to line to line. Okay, one last example. Let's say f of x is given to be something like this. 2 plus x to the 3rd power all over, say, x to the 5th power. Say we're given something that looks like this. Something we could do is manipulate this first to separate it and end up with this. F of x equals to 2 over x to the 5th power plus x to the 3rd all over x to the 5th power. Good. And now this reduces, so this is f of x then equals to 2 over x to the 5th power plus 1 over x to the 2nd power, right? There's 3 copies of x there, 5 copies of x there, 3 of them reduce, giving you just x squared in the denominator. And now when we find the derivative, then we're going to be able to change this like this. So this is f prime of x is equal to d dx of the 2 over x to the 5th power plus d dx of 1 over x to the 2nd power. And we know that we can manipulate these a little bit and get the following. This is equivalent to the derivative with respect to x of 2 times x to the minus 5 power plus the derivative with respect to x of x to the minus 2 power. And so the derivative will be equal to 2 times negative 5 times x to the minus 5 minus 1 plus negative 2 times x to the minus 2 minus 1 So the derivative is equal to negative 10 x to the minus 6 power minus 2 x to the minus 3 power. So the calculus part is over at this point, so this is the derivative. Now we got to use a little bit of algebra to simplify this. So for one thing, we don't like negatives in the exponents, so that means that the derivative is equal to negative 10 over x to the positive 6 power minus 2 over x to the positive 3 power. Okay, so that's one good form of the answer. Or we can also combine these into one big happy fraction. We can multiply the numerator and denominator of this one by an x to the power of 3 over x to the power of 3. Together that gives us x to the 6th power in the denominator, therefore matching. And so we can conclude that our derivative, f prime of x, is equal to one big happy fraction, where we have a minus 10 minus 2x to the 3rd power divided by x to the 6th power in the denominator. Another good form of our derivative. Okay, so lots of examples. Make sure you pay attention to the notation. Please work on making sure that your work is nice and neat, that it follows from one line to the other, that at every step you're making complete and proper mathematical statements. And then be real careful with this notation, right? That's what we're trying to get used to in this section. This little prime thing means the derivative of the function f. And then this notation is letting me know that I want the derivative with respect to x, so the derivative of the function, this one, there, and then the derivative with respect to x of this function, right? So we had a theorem that said that if we have two separate functions that we know are differentiable being added together, we can find the derivative of each one separately and then add them together. That's what allows us to do that. Good. As we move forward and get more and more comfortable with derivatives, we will take, we'll write down less as we move forward, and that's natural and it's expected. So as we move into the more and more complicated functions and deeper into the book, we will naturally skip some of these steps. So instead of, I probably would still do like this step just to make sure I don't forget. Maybe write down that step. I certainly would skip this one and this one. So it's pretty natural to go from here down to here as we move forward and get more comfortable. But for now, I do want every single step to be written out. So if you want full credit on the exam, make sure that you write down every little step. Because if someone goes from here and then somehow jumps to there, maybe they know what they're doing, but I don't know that, right? So you need to convince me. Your job on the test is going to be to convince me that this is the right answer, not just to give me the right answer, but I need to be convinced. So you need to show me step by step how you got to that answer. Okay, all right, so let's do one last one. Let's say a word problem. Okay, an object moves along the y-axis marked in feet so that its position at time x in seconds is given by this function. F of x equals to x cubed minus 6x squared plus 9x. A, find the instantaneous velocity function v. B, find the velocity at x equals to 2 at x equals to 5 seconds. And C, find the time and the velocity equals to 0. Okay, so if this function, f of x, given by this equation here, is the position function, it means that the input is time in seconds, and the output is a distance. We learned before that when we take the derivative of a position function, we get the velocity function. Okay, so part A, find the instantaneous velocity of the function. The instantaneous velocity function v really just means to find the derivative of the position function. Remember that the derivative function is also thought of as the instantaneous rate of change. So if we look at a position function and we want to look at the instantaneous rate of change, that is exactly what velocity is. So that would be the instantaneous velocity at a given point. So for part A, all we really need to do is find the derivative. I'm going to let v of x equal the velocity function. At time x. So v of x, the velocity function, is equal to the derivative of the position function, which means that v of x is equal to f prime of x, or that v of x is equal to the derivative with respect to x of the function x cubed minus 6x squared plus 9x, right? All those mean the same thing. So let's go ahead and find it. So the derivative then is going to be equal to the derivative of x cubed minus the derivative with respect to x of 6x squared plus the derivative with respect to x of the 9x, which means that the velocity function equals to 3x squared minus 12x to the power of 1 plus 9, right? Or 9 to the power of 0. We have a 1 there. We subtract, we bring down the 1. Well, okay, just to make sure it's clear why it's a 9. Following the rule, we can think of this as having a 1 there, and then we bring the 1 out in front, and then multiply it to the power of 1 minus 1. So that means that that simplifies as the velocity function equals to 3x squared minus 12x plus 9x to the 0 power, which then becomes 1. So then the velocity function is just equal to 3x squared minus 12x plus 9. Right, so that's the answer to part A. The velocity function. So input a time, give me a time value x, and we plug it into this equation, and the output would be the velocity at that time. Right? The f of x function will give you the position at that particular time, whereas this one gives you the velocity at that particular time. Okay, part B says find the velocity at x equals to 2. Well, that's easy. So now part B, when x equals to 2, right? So we want to find v of 2. Well, luckily we found the answer for the velocity function. It's right here. Let me zoom out. So v of 2, just following these instructions, is equal to 3 times something squared minus 12 times something plus 9. And the thing we're going to input is this 2. So that would be a 2 there, a 2 there, and a 2 there. So v of 2 equals to 3 times 4 minus 24 plus 9. So v of 2 equals to 12 minus 24 plus 9. So v of 2 equals to negative 12 plus 9, which means that v of 2 equals to negative 3. Okay, and then the other one was when x equals to 5. So now when x equals to 5, we'll have v of blank equals to 3 times blank squared minus 12 times blank plus 9. And now this time that blank is going to be a 5. So put a 5 there, a 5 there, a 5 there. And so we get that v of 5 equals to 3 times 25 minus 60 plus 9. So v of 5 equals to 75 minus 60 plus 9. So v of 5 equals to 15 plus 9, or v of 5 equals to 24. Okay, so what does this mean? At timestamp 2, so at 2 seconds, at timestamp 2, the velocity is -3. So that means that the slope is negative. We'll see the graph in a little bit. At timestamp x equals to 5, at 5 seconds, the velocity is 24. Okay, don't confuse that with the position of the object, which is then given by this equation. So if we plugged in a 2 into this equation, we'd get the position. Or if we plugged in a 5 into this equation, we'd get the position at timestamp x equals to 5. Okay, the last part, part C, is find when the velocity is 0. Okay, so to figure out when the velocity is 0, we need to figure out for what value of x is this going to be equal to 0. Part C. Find x such that v of x equals 0. So we just need to solve this. 3x squared minus 12x plus 9 equals 0. Okay, so let's try and factor out what this is. So I'm just going to use the guess and check method. Because the first term is 3x squared, I'm going to guess that it's going to be 3x on one of them and x on the other. And then because the last term is 9, I'm also going to guess that it is 3 here and 3 there. Let's see if that works, and there, kind of play around with the plus and minus to see if that's going to get me my answer. So that gives me the 3x squared, and then I get a plus 9. Okay, so let's make them both minuses. Looks like that'll work. So let's put a minus here and a minus there. Let's see. That gives me 3x squared minus 9x minus 3x gets me to minus 12x plus 9. Okay, good. So using the guess and check method, we figured out it equals to that. And now we can break this up a little more and say that this is 3x minus 1, x minus 3 equals 0. And so now, by the zero product property, that must mean that either this is 0 or that is 0. So let's come up here and say that either the x minus 1 is 0 or the x minus 3 is 0, which means x equals to 1 is one solution, or x equals to 3 is another solution. Right? So what we have found is the two places where our velocity is going to be 0. If I want to check it, then I want to confirm that if I plug in a 1 into my velocity function, that I'm going to get a 0, or that if I plug in a 3 into my velocity function, that's going to give me a 0. Okay, so let's begin by graphing our original function, f of x equals to x cubed minus 6x squared plus 9x. So that's the position function, and if we graph it, it'll look like this. Here it is. So here's my position function over time. So if I have a point on my function like this, as the input time x changes, we see the position will change. So it looks like the function starts off at 0, 0. So at time 0, distance away from the starting line, let's say, is 0 feet away. Half a second later, you're this far away. Looks like you're about 3 feet, maybe a little bit more than 3 feet. Let's find the actual ordered pairs, actually. There they are. So half a second later, you're 3.125 feet away from the starting line. And then 1 second later, you're 4 feet away from the starting line. and then 1.5 seconds later, you're getting closer to the starting line. So you've turned around and you're kind of walking back toward the starting line. And then 2 seconds later, you're only 2 feet away from the starting line. And then 3 seconds later, you've come back all the way back to the starting point. And then you start up again. So 3.5 seconds later, now you're 0.87 feet away from the starting line. 4 seconds later, you're 4 feet away, and so on and so forth. We can see that now it begins to just grow out of control as time goes by. So the only part that's interesting is right here. And since we're letting x equal to time, usually we only consider time starting at 0 moving forward, but depending on the word problem, we might consider time to be negative, meaning that it's before a particular point, right? So if t equals to the number of minutes past noon and you get a -3, then that's 3 minutes before noon. So it depends on the word problem, but often we let the time only be positive, so that might be the case here. Okay, so now if we're interested in the velocity, remember this is position. This means that you were 3.25 feet away from the starting line half a second later. And this means that you were 4 feet away from the starting line 1 second later. So if we want the velocity, we need the tangent line, right? So let's look at the tangents. There they are. So these are the tangents. The slope of the tangent will give me the instantaneous rate of change. And because we're looking at a position function, then the instantaneous rate of change will be the velocity. So the slope of this red one will be the velocity at that timestamp, right? So at half a second later, you are 3.125 feet away from the starting line. And how fast are you going? You're going the slope of this red line. I don't have it written down here, but when we find that slope, that will be the speed at which you're traveling, the velocity you're traveling at this point. Also note that the slope is positive, that means the velocity is positive. Okay, and then you climb up to here and we see that the slope is going to be 0, it's horizontal. And then we begin to go this way. Notice that the slope becomes negative, and this is a case where you started to walk back toward the starting line. At 1 second after you started, you were 4 feet away from the starting point, but then 3 seconds later, you were back to the starting line. So you traveled away and then you traveled back to the starting line, and then you started to go away again, so the slope becomes positive. Okay, so this question asked about the slope at time equals to 2, v of 2. V of 2 we found to be -3. That means that, well, let me confirm, v of 2. Yeah, v of 2 was equal to -3. That means that the slope of this line right here is equal to -3. And then we also worked with 5. So let me zoom out a little bit more. And we found that over here at t equals, or x equals to 5, we also found that this slope was equal to 24, a positive 24. Okay, so when x was equal to 2, that means at 2 seconds, your position function is at 2. So you're 2 feet away from the starting line. And your velocity is at -3, and we're dealing with feet per second. Feet per second. And the negative means that you're traveling back toward the starting line, right? So you see how this is going back toward the starting line. And then you arrive all the way there. So at x equals to 3 seconds, you're back at the starting line. Okay, and then the next part of it said, well, what about x equals to 5? Okay, so when x equals to 5, after 5 seconds, the object is 20 feet away from the starting line, and its velocity is positive 24 feet per second. That's what that interpretation, that's how we can interpret that, right? And notice it's a positive slope, so it's traveling away from the starting line. Okay, we were also asked to find when the velocity was equal to 0, and so we see that the velocity equals to 0 at x equals to 1 and at x equals to 3 after 1 second, or at the 1 second mark, and at the 3 second mark the velocity was 0. Let's look at the graph. Look what's happening around there. At velocity 3, see how the horizontal line is 0, the slope is 0, therefore its velocity was 0 there. And also over here at this point the velocity is 0, right? So if you're traveling away, right, away from the start line, and then all of a sudden you start walking toward the starting line, your position comes to a stop, and then you start walking backwards back toward the starting line. But at that very second when you changed from walking away, and then change to walking toward the starting line, back toward the starting line, you got to reach to a point where you're not moving for a fraction of a second, and at that point the velocity is 0. Same thing over here, you're walking back toward the starting line, and all of a sudden you start walking away from the starting line again, which means that at that very moment you're not moving at all. So that's why it makes sense, hopefully, that the tangent line would have a slope of 0, right? So these are the two places where the velocity is 0, the horizontal line, the tangent line is horizontal. Okay, hopefully that makes sense. Okay, one last example. Let f of x equals to 3x to the third power minus 2x squared plus 5. Find the derivative function, f prime of x. And then part B, find the equation of the tangent line for x equals to 1. Okay, so part A is going to be pretty easy, hopefully, at this point. F prime x is equal to the derivative of this thing, so d dx of 3x cubed minus 2x squared plus 5. And so we know that we can just take the derivative of each one separately. So this is just going to be 9x to the second power minus 4x to the first power plus 0. So we can just ignore it. Or we can just put it in there. Plus 0 for that one. The derivative of a constant is 0. So f prime of x is just 9x squared minus 4x. Okay, that's the answer to part A. So this is an equation. The derivative is an equation that generates for us the slopes of the lines that are tangent at the input values. Okay, so now for part B, find the equation line tangent at x equals to 1. Well then, if we just plug in a 1 into here, we'll be able to find the slope of the line tangent at that point. So for part B, we're going to first of all find f of 1 so that we can find the ordered pair on the function. So that would be 3 blank cubed minus 2 blank squared plus 5. And so we're going to put a 1 in there because we're dealing with x equals to 1. So if we simplify that, we get f of 1 equals to 3 minus 2 plus 5. So f of 1 equals to 6. So we have the ordered pair 1 comma 6. The ordered pair 1 comma 6 is the point on my function, and we want to find the equation of the line tangent to this point. That's the whole goal. Okay, so we have a point. Now we need the slope of the line tangent at this point. To find the slope of the line tangent at this point, we're going to use this. So now if we do f prime of 1, 9 blank squared minus 4 blank, we'll get that if we put a 1 there and a 1 there and a 1 there, we'll get our answer. So f prime of 1 is going to be equal to 9 minus 4. F prime of 1 is going to be equal to 5. So I know that the slope at that point of the tangent line at that point is going to be 5. Okay, so now I can use the point and the slope to find the equation of the line that's tangent at that point. So now we use y minus y given is equal to m times x minus x given, and we're going to use the point 1, 6 as the given point. So it's a point that's on the line. And we know that the slope is equal to 5 at that point. So now we just plug this into here. This is y minus 6 is equal to 5 times x minus 1. And then we simplify. We get y minus 6 is equal to 5x minus 5. Add 6 to both sides, and so we get y equals to 5x plus 1. Add 6, we get a plus 1. And there's the equation of the line tangent to our equation at that point. Okay, so given an equation, f of x, we can find its derivative. Hopefully that's pretty easy at this point, since this is a very straightforward derivative. It's just a simple polynomial. We know that when we have terms that are separated by addition and subtraction, we can apply the power rule to each one of them. So you apply them separately and then add them or subtract them when you're done with that. Okay, so we saw plenty of examples to kind of break down that a little bit more. So here I kind of skipped some of those steps and just kind of streamlined it a little bit. So hopefully that's clear of how we find this derivative. Once we found that derivative, then we needed to do two things. We need to find a point that we're interested in. They said find the equation tangent for x equals to 1. That's why we used the original function evaluated at 1 to give me my ordered pair. And then I use the value x to the and apply it to the derivative function to find the slope of the line tangent at that point. Right? That's what the derivative function does. It gives me the slope of the line tangent to that point. Okay, so let's graph this. Okay, so here is our function in blue. Here's our original function. And then when x equals to 1, we get the point 1, 6. And then we need to find the equation of this tangent. We found out that the slope was 5. And after we did a little bit of work, we found out that the equation of that red line is equal to y equals to 5x plus 1. There it is. Let me change the color. Okay, so confirming that it matches. So here I have the general tangent as it travels through our function at various points. So if I just stop it there at 1, then that's my tangent line. I want to find the equation of that line. And I can confirm by typing in the actual equation that I found, y equals to 5x plus 1, and you see that it does in fact equal to that value. Okay, so that should be more than enough to get your homework done. So please try the homework out and let me know if you have any problems, questions, or issues. Stay in touch.